Start the presentation. Can you see the presentation?
Yes, sir.
Yes,
Okay.
sir.
So these will be the topics of today's lecture. Actually, this will be a kind of extension of what Professor Basu taught in two of his lectures. Mostly it will focus on the discussion with respect to the UNIX type operating systems or Linux. And here we'll be talking specifically about the states of a process, of a UNIX or Linux process. And he basically gave the overview of generic state transition diagram, the suspended state, the running state, the ready state, created state, terminated state, like that. So here we will see that if the same number of states are actually implemented by the designer, or they have added few more to have a better understanding of the system. So this will be one objective. So at the end of the lecture, you'll be able to visualize how a Unix system designer, operating system designer, defines the process states. And in Linux, you find that sometimes it says zombie, suspended, running. So how it is related to the Linux states that it shows in the ps command. And next we'll talk about the Unix process data structures. So what we found, again, he also talked about the process control block, the PCB, right? So the PCB is actually the, the area or the kind of entry which stores the details of a particular process. Okay, because what we found is a process is a dynamic entity, a program is a static entity. If it is compiled and if we execute it, it becomes a dynamic entity. And once it is dynamic, it requests for resources, memory, CPU, other IO resources, and it will utilize them, and it will make changes in the registers while it is running in the CPU mode, while in the running state, while it is waiting for some event to occur. So that event also need to be tracked, that for which particular event it has been blocked or suspended. If it has terminated, what we found is you cannot simply remove the entry of that process. You have to hold it for a while till the parent responds. And we found that such processes are called zombie. So like this. So the objective of the operating system or the OS designer is to keep track of all such information in some data structure. So that is what we call as process data structure. So in the PCB, what he mentioned as PCB, we'll see that what exactly are the fields of a PCB in a real operating system design, and how the whole thing, because it will occupy some memory, and we know that memory is not, it's about virtual memory in a typical time-shared multi-programming environment these days. So how the whole thing is tracked by the process through the process data structure. So that we'll see. And finally, we'll try to see that what we mean by the context of a process. So what exactly, because from the process data structures, we'll find that which part need to be saved during a context switching or need to be loaded. So that will be the outline. So the whole discussion will be in the say in terms of Unix or Linux type systems. So that is the only change. So there will be not too much of concepts that will be added. Rather, we'll have more precise information. And you can refer to these two books, and I have mentioned the pages also from which you can refer to today's discussion. And the PDFs are already provided to you. So before we get into the process states or its state transition diagram, let us just quickly review two very basic concepts which we'll be referring during the process, during our discussion. So I prefer to talk about it prior before switching to those details. So first we talk about the user and kernel stack. So I mean, till now we have the term stack is familiar to us. We know that whenever we talk about a process or a program, say for example, when it becomes a process will have its entire the contents of the process or the physical contents of a process. It will be in terms of 4 segments. So this we know from our previous year course, and I think those who have done C, C++, they also know that whenever we write a program, so the whole program, the contents, the source code, the global variables, the local variables, the space from the heap. So everything that is associated with the process, it is organized in form of 4 segments. It is a code segment, data segment, heap segment, and stack segment. So this stack is basically the user stack. So in a case of operating system process, I mean, when we say in terms of Unix or Linux process, we already know that the running, when a process starts running, it can be in 2 different running modes, and those are the kernel running and the user running. So it's the kernel running and the user running. So in the user running, we know that if the process is executing some user level libraries like sum or subtract or sinx, whatever, so these it will just keep on executing in the user running mode, user mode, because during those it will be mathematical, arithmetic operations, logical operations, and it will not require any specialized privilege to access system resources. However, if it wants to display the result of the operation or the outcome of a function, the sinx, then it will call printf, and the printf requires intervention of the kernel or the operating system, because this will require access to the display, the monitor, that is a external hardware. So in that case, when you call printf, scanf, or say fork or get PID, any such calls, function calls, they in turn will make some system calls, will trigger some system calls. And whenever there is a system call, that means through those system calls, we are asking the kernel to execute some specialized functions to provide that service. So it will be running into the kernel running mode. So any user process during its lifetime or while it runs, it can be either in the user running mode, and as and when required, it will go into the kernel running mode, get its work done via the kernel, and will return back to the user running mode. So that is how it works. So the key point is, in such a case, when we think of a user process, say in this case, this is main calling f1. F1 is a user function. F1 calls fread, and fread also is a user level function. It's a wrapper to, say for example, sysread. Sysread means a system call corresponding to a file read. Say, let us assume that. So this is a system call, and this is the wrapper function, user level library, which wraps this. So this is also a user level function, and this is a user level function, but this triggers a call to the system module or some system functions. So here sysread is purely a kernel level module or a function which is executed, which need to be executed in the kernel mode, and that probably it calls some other operating system module, say request inode. So we are not interested about the details of it. Say request inode is here, and that too is a kernel level function. So when we start this process with by just executing main, so main calls f1, f1 calls fread, fread calls, so like that it goes on. And what you mentioned is So the point is here, any process in Unix or Linux, they will maintain two different stacks instead of a single stack, because there are two running modes to deal with the series of function calls, because we know that stacks are required whenever there is a series of function calls. F1 calls F2, F2 calls F3, F3 calls F4, like that. So as the functions keep calling the another one, in the stack we have to store the context or the return address, everything in the stack, so that once the function is called, it completes execution from the stack, it will pop out and it will return back to the calling function. So that is the requirement of stack. So if any process will have, so the idea is any operating system, any process in a Linux or Unix operating system will maintain their individual user stack as well as kernel stack. So the point is every process will have its user stack and kernel stack. And say for example, this program, when it runs into a process, it has got its, this is a user stack, this is a kernel stack, and these two are separate stacks. So why we have why you need to have separate stacks, we'll see it shortly. And say this is a stack pointer. So stack pointer, we know that this is a kind of in the CPU registers, when it starts running in the CPU register, there is a special register which keeps track of the stack pointer value. So if it starts, so this yellow line shows that you are about to jump to F1 and you are in the user running mode. So it's user running mode. So here, when it jumps to F1, the stack pointer points to this user stack, and as we can see, it has pushed the context of F1. Sorry, the context of main. It will be the context of main. There's a small mistake. It is the context of main, and the stack pointer points to this. So the stack, because it is in the user running mode, the stack pointer points to the user stack, the top of the user stack. And from there, if it calls fread, so this is where it calls, and here it should be the context of F1. So there's a slight mistake. It should be context of main, it should be context of F1. So the pointer points to this one. Now it is about to make a system call, or it will be accessing some operating kernel modules. So when it calls this, it is within this sysread. Now the point is it will save the context, or you can say the user level context, because it has now switched from the user running mode to the kernel running mode, and it will save the user level context. But which stack we should use now? It will use the kernel stack because it is in the kernel running mode. Okay, and the same stack pointer in the CPU will be pointing to this top of the kernel stack. From there, if it executes or calls this request inode, which is some statement, it will jump here, and before it jumps, it will save the status of sysread. So this is correct, this stack contents. So the context of sysread will be pushed here. So once this completes the execution, it will just be the reversal of it. It will pop out, it will return back here, it will pop out from this, and it knows where to jump back. It will be, now once it moves from the kernel running mode back to the user running mode, the stack pointer will start pointing to the user stack instead of the kernel stack, the top of the user stack. And then it makes returns to the main, and there it stops. So this is how a particular process will maintain two different stacks and will use it during execution of a series of functions, both in the user mode and the kernel mode. Now the point is, why we need to require two different stacks? Why not one particular stack? The same user stack is enough. Can you guess this? The reason is very simple. The point is, we know that the stack that we generally understand, that is a stack segment of the stack, that stack is basically the user stack. So till now, the stack segment that we generally know is the user stack. So the user stack, user is free to write anything in that and try to change the top and everything, because like you can make changes in that also, the contents. You may not able to change the stack pointer, but you can change the contents of that stack. So if you would like to use the same stack to store the kernel routines, the whenever the kernel routines are getting executed in some sequence, then there might be a problem that you intentionally or a user maliciously it tampers the contents of the stack frames or the entries of that stack and forces it to jump into some unwanted locations, and that might create a whole problem and the whole OS might crash in that case. So to avoid that, and in fact the OS operating system has no control, because operating system does not control about the contents of the user stack. User stack is purely maintained by the user, and the user can free to is free to change it also. To have its own control, the kernel expects the user or requires the user to maintain a separate kernel stack which it can use during the kernel running mode. So this is the story of stack, user stack and the kernel stack. And the next concept is a signal handling or signals in operating system. So before we start the state transition diagrams, so these will be some of these terms will be referring. That's why uh, I'm trying to go through these terms. So signals, the term is pretty well known in our real life. Say for example, say I'm taking a class. I'm not talking about this virtual class. I'm taking a maybe a physical class, okay, or maybe in the same class itself. So the next faculty, so I know that somebody else will be taking the next class. Maybe the HOD will be taking the next class, okay. So what has been agreed that if I send her one missed call, like one ring, then she knows that maybe that because of some noise, because of some problems, I am sending that signal. Now I may just ring twice, so it rang twice. If she finds a missed call of two ring to uh, where it rang twice, maybe the implication is that I am about to complete my class, and then it's just to alert her that you can start the class within another 5 minutes. But if I make three missed calls, if I give three missed calls, then that may be something serious. Like I want to convey that the internet connection suddenly dropped, so I have to abnormally abort the class, okay. And maybe if it is there are 4 missed calls, it may be that there's a fire broke out, or something extremely serious. So the point is, in our real life also, we try to convey through some signals, we try to communicate with others. And in the case of operating system also, processes often send signals to each other. Sometimes the kernel sends a signal to a user process. Some user process P1 sends a signal to some other user process P3, and P3 sends something. So like this. So processes interact with each other, communicate with each other using signals. Okay. So signals are basically a form of inter-process communication, because when the processes coexist in the operating system, concurrently they are getting executed. So the processes may not be related via maybe parent-child relationship, but still they may be they may require to send signals to each other. Okay, so this is quite common, and for this, during say 1970s, in the right from the inception or from the basic versions of Unix, this feature of this way or mechanism of inter-process communication got implemented. So signal handling or signals. And the thing is, the operating system designers defines a finite set of signals, and this is generally 64 in case of Linux. So you have got 64 signals that is defined, and each of the signals they have got some meaning, as you can see here. So I've got a few 4 or 5 such signals listed here. So SIG stands for that, it's a signal name, it's a macro for that, it's a symbol for that. It's for abort. So if some process receives this SIG ABRT, it will abort, it will simply terminate. SIGINT, it's a signal which is generated when I press Control C. You all found that if I run a infinite uh, uh, infinite loop for a process from the terminal, it keeps going, and if I have to stop it, what should I do? I just press Control C. So when I press Control C from the keyboard, it actually uh, means that I'm asking the operating system kernel to, so it's basically a keyboard interrupt, we can say. It's a hardware interrupt, but that hardware interrupt is actually, uh, mm, so when the kernel finds that this is a hardware interrupt, it immediately delivers the SIGINT signal to the foreground process corresponding to that terminal. Got it? So whenever there is a interrupt occurs or any kind of event occurs, then such signals may be uh, issued by some process meant for some other process. So it may be the terminal interrupt, and you can we'll see later on, we'll discuss in more details. I'll have 1 or 2 classes on signal handling, but we'll find that using a software say statements, I mean some system calls also, how can we trigger this uh, signal which is equivalent to this pressing Control C to terminate a process. Okay, there may be other signals also, like invalid memory reference, or if the file size exceeds. So a process, the maximum size of the file that it can create, it also got a limit, and if it exceeds that, there is a kind of error and it to be stopped. So if that event occurs, that it is trying to exceed the maximum size limit of a file that it is meant that it is been allowed to, then also the kernel will issue a signal to that particular process. And because, as I mentioned, so if you give 1 missed call, 2 missed call, 3 missed call, like that, so based on that, uh, the process knows that what it's meant for, I mean what it need to do. And generally, once a signal is delivered to a particular process, who delivers? The kernel delivers. Then some actions need to be taken. So whenever the process, if the process is in a suspended state, it is not actively running the CPU. So whenever the process becomes active or it is scheduled, then the first thing it does is it checks whether there are some signals which are kept pending, which need to be some actions need to be taken. Okay, and whenever, what kind of actions there are for the signals, there are some default actions. So default action means if you press Control C, there is nothing can be done, so it will be simply terminated. That's a default action. But the user can, the nice thing is, the user can define its custom actions also. Okay, so if I press Control C, I can make the arrangement. So we can write that code like a foreground process which is running in the terminal, and if it's an infinite loop, and if I press Control C, nothing happens. Okay, so this code I'll write, it's a very simple code. So the thing is, how it is possible, the process, if it has willingly set some non-default action, some custom action for that signal, so nothing will happen. I mean, it may be nothing happen, or just displays why you interrupt me, so something like that. So these things can be done. So we'll see the details. So the point is, this signal handling is something very essential. So any running process may receive multiple signals from multiple processes, and a particular process can send different types of signals to a particular process. So the operating system kernel need to keep track of this also. So these signals that are received but not yet handled, that information need to be stored, as well as the actions that the user has defined, whether it is default or something that some custom actions has been defined. These information all need to be stored by the operating system kernel. So the kernel data structures that we'll be discussing shortly, we'll see that these informations, some information related to this will be there. Okay, but again, the details of how the signals are generated or issued, what is a system call to generate a signal, if somebody wants to issue a signal, some process, and how we can redefine its action. All these details will be discussed later. Now let us come to the Unix process states. So here we find that definitely there are 4, 8, and 9. So there are 9 states that has been defined. So that has been defined by the Unix designer, Unix operating system designers, right from 1970s, 80s. So this philosophy defines like this. So it is not that 4 or 5 states, rather there are 9 states. And as you can see, there is a striking difference. So now it has defined 2 running states. So the Unix designer is willing to distinguish between 2 different running states of a process: user running and kernel running. But maybe there is some other operating system which just defines it to be just one of them. I mean one. But the Unix designers, because of the privileged mode and as well as the user mode, it has distinguished it as 2 different running states. You will have the zombie. We already know what zombie means. After it gets terminated, it becomes in a zombie state. Created means after it has just been created. There are various ways to create. We can call fork system call. The parent can call to create. We can just execute ./a.out. So there are various ways. Whenever we try to open a terminal, want to create a new terminal, the terminal process gets created. So there are various ways a process can be created. And as you can see, this is asleep in the primary memory. This is asleep in the secondary memory. So these are probably the why a process becomes asleep, because it is suspended and it is waiting for some kind of event which has not occurred. So this event can be that it has requested for some memory, but the memory is not available. It has requested for some disk record, but probably that has been locked by some other process. We found the problem of synchronization. So some file has locked and it is doing some operation, and meanwhile if some other process has requested, simply it has to wait. It may be that I mean it may also happen that a particular process is expecting some signal from some other process, and without that signal, so signal means maybe the go ahead signal. Okay, so the child is or the parent is waiting for the child to complete something, some subtask. So there can be many such events which uh, requires that a process remains asleep or suspended. Now the process is suspended, but if the process stays, some portion of the process stays in the primary memory, we try to identify it through this state. Whereas if the process is in the secondary memory while it is suspended, we identify it with respect to this state. And this ready to run, as you can all recall, that this corresponds to all the processes which are just waiting for the scheduler to schedule it. Okay, and they might have formed a circular queue and they are all waiting. So they are not waiting for some IO. They are not waiting for some any kind of resource. They are all just waiting for the CPU to be assigned to them. And because it is time shared, they all know that within a finite delay, the CPU will be switching from one process to other, and eventually they will get some chance to get executed. So this is a queue. So this state means the process is enqueued in that ready queue. Same that in case of preempted. We will come to it later on. So here means it is ready to run. It is in the ready queue, but the process is not in the primary memory. Now, what may be the reason why the process is ready, but still it is not in the primary memory? So the reason may be that you have initiated too many processes, and it becomes difficult to accommodate them, to get to accommodate or to allocate sufficient space for each of them. And that's why the memory management module, the swapper process corresponding to it, it has decided to swap out some of the processes. uh, I mean, it has to take that harsh decision that even though they are ready, they will be swapped out from the primary memory. But that's to accommodate, because the process which is running as you know that it needs to have sufficient number of pages in the primary memory frames. Otherwise, there will be a huge number of page faults and it will delay the processing. So there can be various reasons and policies based on which a process, either it is ready, even if it is ready, a process may be swapped out in the to the primary secondary memory or disk, or if it is in a blocked state, suspended state also, it will be swapped out in the secondary space. So these are the implications of the different process states. The details are here. This table has been copied from Stallings. Page numbers are given. So now let's see that these are the kind of events or the reasons for the transition, you can say, the actions which triggers a change from one state to other. So let us consider the created, start from the created. So which of these can trigger the trigger this particular state? Which of these actions among these can trigger this created state?
Fork, sir.
Can anybody say? Fork? Simple. So there can be other reasons, but as per the the cases given here, it can be fork. So it's fork. So what this created means? Created means once you are creating a process, even a child process, we know that once it is created, the child wants its individual identity, right? So it wants it to be isolated from the parent itself. So the parent is having its heap segment, code segment, data segment, stack segment, but the child says, I want my own segments, all the 4 segments of my own. Now you may copy it, but I want it. So the thing is, the first thing that a created process will ask for is what the created process will require. So what a process creation means, a process got created. So what can you expect from it? What does it mean? Created means the first thing. So it's just like a student has enrolled. So you have just came to the institute and you have enrolled your name. So you have just paid the fees and you got a registration number, etc. So the thing is, this means the process has just got an entry in the process table. So it has a process table entry has been created for it. So you have got your registration number, you have got your enrollment number and all these details. But that does not mean that you have got so you have got your hostel room, right? So this created means you have got your entries, you have got your registration numbers, roll numbers and all these, but you are yet to get your hostel room. Now what might happen that if there are enough rooms in the hostel lying vacant, you might get a room, and if that is not the case, you have to, maybe this is that you have to commute from your home, like that. So the thing is, if there is enough memory, the process which is created, it becomes in the ready state. Ready means it is about to be scheduled. It's in the ready queue. But this means it is in the ready queue, but also in the primary memory. But this means, so from the created, it can be although it is ready to run, but the thing is that process can be in the primary memory, in the secondary memory, because there is no enough primary memory available for allocating some space. Okay, so both can happen. From this ready to run, what can happen? A process which is ready to run, what can happen now? Which event can occur?
Sir, user running or kernel running?
No, so what do you expect from here? Where which state should be, there will be a transition to. So from ready to run from this state, where there can be a transition. Can it make a transition to both of these and this?
Kernel.
So one of them.
Kernel.
Hello. So can it directly jump to user running? Is that possible?
No, sir. The kernel.
See what fork is. Fork is a system call. Hello. Is that possible?
Sir, I
can
think
it directly jump to user running?
I think it has to go to kernel running first.
Yes, I'm not getting. Yes or no? It has to go to kernel running.
Yes.
See,
sir.
the point is, uh, see, the point is how it got created by calling fork. What is a fork? Fork is a system call. So through the system call, when the system call is executing, the kernel actually allocates one entry in the process control block, and then it makes different initializes the values and all this. We'll see. Now it is in the, and it makes an entry in the ready queue. So now it is not yet finished. The fork has not yet been finished, right? Because the fork will need to return something. So the fork need to return something. So the fork is basically a system call. So the fork system call is not yet completed. So from here, it must go to the kernel running first once it's rescheduled. Because whenever it is coming to this path, it is still in the in the execution of that fork system. So from that kernel running, if it is scheduled, so if it has successfully, maybe the first it's a newly created process. So from the kernel running, what it will do now? It will switch to the user running. Definitely, if there is enough time, let us assume, because the time slice is there. So if enough time is there, so it will switch to the user running mode. So when it comes from the user running mode, means it has just returned from the fork. And if it is a parent, you know that it will get the PID of the child. If it is a child, it will get the value 0 return from the fork. Okay. So while it was running in the user running mode, so what can happen? So being in the user running, what can happen? What events can happen?
Preemption.
Sir, it can be preempted. It can go to the sleep state in secondary or primary.
The first thing is, whatever you do, what happens? Like, the thing is, if you are running simply, you are making, say, uh, 2000 additions, keep on adding like that. So you don't care, you just want to use it as long as you want, but that is not possible. So the thing is, the first thing that can happen is immediately there will be a timer interrupt that will stop the process to continue forever. That is one possibility. Other possibility is the user process can execute a printf statement that it wants to print something in between. So if it prints something, if it wants to print, means it requires the there will be a system call corresponding to that. So printf will trigger some system call. So system call means what? It is basically triggering a software interrupt, right? So what else it can do? There can be other software interrupts. Maybe that the process, after few additions, it can decide to fork one more child. So the child will do the rest of it. So that also is a system call. So, and the system call, as we know, it's basically it's implemented as if it is a software interrupt. So what can happen here is the user running process may either be interrupted because of timer runout, or it may trigger some system calls, or it may trigger some software interrupts in form of system calls. And what else it can do? It can also execute just exit system call, because it has completed. It is no longer so it is just like adds I equals to I plus 1, and then it stops. So it can execute exit system call. So whatever it is, so there can be either some system calls that gets triggered, or there can be some interrupt. It can be a simple timer interrupt, which can again, so if there is an interrupt or any kind of system call from the user running, the first thing is you need to switch back to the kernel mode. So the preemption, it cannot go to the preempted mode first. First of all, it must know that what has happened. Okay. So either it is terminated. So from the kernel will try to find out what has happened. So if so, the first possibility is maybe that the process has called exit, the exit system call. Then which state it will make transition now from the kernel running? If the reason is this system call is exit system call that has been executed in the user running, and then it is here, then where it should jump now from the kernel running?
Zombie.
Zombie. Because exit means the process will die, but its status, I mean sorry, its PCB will not be removed. It will have entry in the PCB. It will that will remain for its parent to read the information. contained in it. What can be the other case? Like if it is not the case, if the case may be that it has received a so here being in the kernel running mode, while it was trying to find out what happened, what went wrong, there may be some other interrupt that came corresponding to that process. So what can it happen? Like, so these are all the details of the different ways, different reasons for termination. So I'm skipping these details. You can get it from the Stallings book. So now, being in the kernel running, there can be some more interrupt that comes, and interrupts keep coming, and based on the priority of the interrupt that will be served. Okay. So because during the interrupt processing, it will be all running in the throughout in the kernel running mode. Okay. Now at some point of time, definitely it will be uh, so this system call is over probably. So whatever the interrupt came, the interrupt has been served. So now it may happen that from the kernel running mode, if say for example the IO is has not yet expired, it will again return back to the user running. Okay, but while it was in the kernel running and it is ready to just to move to the user running, there is a IO interrupt. Like this interrupt can be being here, there is a IO interrupt, but it was just about to move to the user running. Then what will happen? So it cannot go to the user running. So from the kernel running, what do you expect? The process
Preempted.
was in kernel running. Huh? Which one?
Sir,
Where it should
preempted.
jump? Yes, the thing is it should actually move to the ready state, right? Because now it is ready for scheduling and a timer interrupt has stopped it. But the thing is, the Linux designers, they prefer to uh, distinguish it as a different state, and that is preempted. So that's why in that case it will be going switching to the preempt state. And this dashed line says that this preempted is nothing but it's the same as ready to run in memory. Okay. So what is a preempted? What is the difference between preempted and ready to run? So they are basically the same. They contain so the processes which are in the ready queue. So both of them actually refer to the processes which are in the ready queue. But the processes which were just about to jump from the kernel to the user running will be denoted as preempted in the preempted state. So from the preempted state, which way there should be a transition? It's about to get the CPU. Whenever it's scheduled from the preempted where there will be a jump, which state? A preempted process. Preempted means process is returning from the kernel to the user mode, but the kernel all sorts it was completely ready. So if it is scheduled a preempted process, so where it should jump, it will return to the user running. So that way it goes on. But the other possibility in the kernel running is that you have asked for some say fread or some kind of disk access. Okay, and for the disk access, what requires, you have to know whether the disk is available or not, if the disk is now busy, or you have requested for a file record, the file record is blocked. So for all these, some kind of maybe you have requested for some IO operation and the IO is busy. So for that, the process need to be in the suspended state, asleep state, or blocked state. But it is in the second but it is in the, sorry, there's a mistake here. It should be in the primary memory. I'll correct the mistake. It should be in the primary memory. Okay, these two in the primary memory, these two in the secondary memory. Okay. So from there, if the reason for which it was waking, it is now resolved, the reason is gone, then it will wake up. Wake up means now it becomes again active, and it is ready to be get scheduled. So it will join in the ready queue. Again, it will take an entry in the ready queue. Or being here because of the lack of memory space, the operating system memory management may decide to swap it out in the secondary space. And being here, if being here the event for which it was waiting is over, then we would expect it to again wake up, but it will still remain in the secondary. Okay, it will be in the ready. Its status will be made ready, but it will be in the secondary, and from the secondary, depending on some policies, at some point of time it may be swapped in the primary memory, and only then it can be scheduled. So a ready queue process which is in the secondary memory cannot be scheduled because there is no point of scheduling. Okay, and even when a process in the ready queue in the primary memory being there also, you can have a swapping out of it. That might also happen. So this is a complete state transition diagram corresponding to the Unix processes. I mean, and more or less the same philosophy is followed in the Linux also. But in the Linux, you see that uh, these are, when we executed the Ubuntu Linux, we found this one snapshot. We found that S, S, R, Z, and these are the number of states. So you don't find each of those 9 states defined here, right? So there is not a one-to-one analogy or similarity of this. But zombie, zombie is this zombie. There's a exact match. But when we say it's running, so running strictly means runnable. That is on the run queue, either executing or about to run. So if it is executing either in the kernel or user, it will be shown as a running, or if it is in the run queue, means either in the preempted or this, so then also it will be shown in the running state. So that is how the Unix the PS command will interpret its state, and then these all will be treated as suspended. Okay, so S is a suspend sleeping. So sleeping, you can be in the primary memory. This is a mistake, as I mentioned, or in the secondary memory, but it is sleeping, means waiting for an event to occur. So in terms of the detailed state transition diagram, if we look into these finite set of states that it displays, this way we can try to find some analogy of these two. But there's some more details, we'll refer to it later on. And in many of the books and documents, you'll find that Linux process states are defined in this form. These are more popular state transition diagram for Linux, specific for the Linux. So this is like this, and I'm not going into the details. You can easily decode it from the text. Okay, so let us now come to the process data structures. So we talked about the state transition diagram, we talked about signals, we talked about both the user and kernel stack. So now let's see. So what was found and what was discussed earlier is that the process, like there can be multiple processes running in the system. They can be user process, they can be kernel process, system processes, but the operating system need to keep track of each and every such process. And when we say it's a process, there are so many things that the operating system need to keep track. So the data structure, or I mean basically maybe you can think of a C structure is defined, which has got multiple fields, and each of the field will refer to a particular information corresponding to that process. Okay, so these colors, say for example, say represent a process table entry corresponding to a particular specific process. Okay, so this is process table. The whole is a process table, and the process table, it has got, as you can see, maybe right now the system is keeping track of, it has got only 5 processes of different colors, and this one is for the specific green process. Maybe, I mean, we are just referring to colors, but they are uniquely identified by their own PIDs. Okay, so what is the first thing that happens? So we are talking about the different information that you need to store corresponding to a process. So what we see that a process will have a distinct state among the different states that we just now explained. It will be either in the running state, suspended state, zombie state, or maybe some other states like this. So the state information need to be stored. You have to store as a kernel the PID of the process, the PPID of the process, parent side and parent process ID, the user ID, the user, uh, the user, some authenticated user who has created that particular process. and the most important thing is the process need to or the kernel need to keep track of the memory of the process. Memory means where its code, data, heap and stack segments actually is. So this is the because it's a virtual memory based operating system, the one that we are discussing. So we'll have this. So this is a virtual address space, say for example, of the whole process. So it will have some pointer to that virtual address space. But does it actually exist, the virtual address space? What we visualize, or what we have a feeling of virtual space, in the in reality, what we have in reality, what we have instead of this. So this is a feeling that the user gets, but what we have actually, and that will be the that is what this process table entry will keep track of. So what we'll have instead of this. In my introductory classes, I have talked about virtual memory organization. So what exactly is there to create this transparency or visual virtualization? What is there? Hello? What we have in the backend, in the background? Can you recall the segment map table, the page map table? Hello? Hello? Are you getting me?
Yes, sir.
Yeah. So can you recall those segment map
Yes,
table
sir.
and the segment map table? So how many? How many segment map tables one process will have? Again, the
Logical
details.
state and physical state.
So the details will be taught by Animesh, but if you can recall roughly how many segment map tables? Just one, and the segment map table will have. You see, it will be pointing to the segment map table, and the segment map table will have entry corresponding to each segment it has got, and any process will have 4 segments, as I'm repeatedly telling. Okay, because it is a green process, I have just shown it on all green. Okay, and each of these entries will point to the page map table, because a particular segment can be consisting of equal size pages, I mean equal size blocks called pages. It may be consisting of 10 pages, it may be consisting of just 1 page, it may be of 2 pages, it may be 3 pages, like this. So the page map tables actually store the information corresponding to the pages of that particular segment. Now what can happen, what we found, some of the pages may be in the primary memory, but some of the pages may not be in the primary memory, and they will be there in the secondary memory. So these page map tables actually point you to either if it is there, if it is one, where it is, if it is not there, where it is found in the secondary. So all these details. So just to have a completeness, I have just shown it. I'm not going into the details of it. That is not the intention. Okay. So this is how it is organized. So basically, the page in the process table entry corresponding to that process, it will have a pointer to the segment map table, and the segment map table will have pointer to the different or each of the 4 page map tables, and the page map tables will like this. This is a whole thing. We generally call it as a memory mapping tables, say for example. So these also need to be tracked, and if you keep track of this one, the rest will be automatically be reached. Okay. So what else you need? What other information you need to store corresponding to a process? This is one that is a new term to you. It is the U area, and U stands for user area. Again, this layout or whatever I am discussing, it is in terms of the Unix operating system philosophy. So we'll find it in the book by Maurice Bach, the chapter 6, or you can also find it in the Stallings book, chapter 3. Okay, and I have mentioned the page numbers. So here, this is the user area. As you can see, the user area is a separate area which is not a part of the process table itself, the process table entry. Okay, so this U area also will contain some useful information corresponding to the process, but the main point is the U area is accessible only if the process is currently running. That is a very striking point. So keep it in mind that this U area portion, all the information that is in the U area, we'll have a brief discussion on each of these. So the information, so the entire information related to the process is some portion is stored here in the process table entry, and some portion is stored in the U area. And there is a link to the segment map table. There is a link to the U area, and the U area also have a backlink towards a process table entry, and that is how it looks like. And the main point is this one: the U area is accessible only if the process is currently running. So every process is having the U area, but it is active, or I mean it can be referred or accessed only when the process is running. And this is not a part of the user's user space, the virtual address space. It is not in the part of the user space, so the user cannot directly access, or even when the process is running, the user itself cannot access directly this U area contents. If you want to know something, you have to make some system call, and through the system call, you will get back the information. Okay. So thing is, if I think of some other process, the blue process will also have the same informations corresponding to that in the same number of fields. It will have a segment map table of its own, and that will point to its separate. So as you can see that every process will have its own segment map table and the corresponding page map tables, and they will then point to the either the secondary or the primary memory frames and all this. And every process will have its own individual U area. Okay, this is the green, and this is the, and why this is highlighted, because currently, let us assume currently the green process is running, but because the blue process is not running, it is still having it, but you cannot access it. I mean, you means the kernel cannot access it. Okay, this is inaccessible, but this is accessible. And maybe in the next time step, or after a short while, if the blue process is scheduled and the green process goes to the preempted state, so this happens. Okay, this means now this becomes active, so the kernel can access the contents of it, and this becomes inaccessible, but still it is there. Okay, so what do you think? I mean, where these say these tables, these U areas, where these will be stored physically, where they should reside in the system, and including this P table, I mean the process table. So the process table is a data structure containing, it's an array of structures you can think of. Then it's pointing to some tables. These tables point to some other tables. So all these tables, this process table, these U areas, where do they reside? Hello? What do you think? Where they should be residing in the system? We have to store it somewhere. Where they should be?
Sorry, main memory.
Which
It's a
memory?
kernel part of the memory.
Where? They should be in the. Hello? I'm not getting. In the primary memory, right?
Yeah.
Because in the secondary, if you store them there, you cannot access it unless you bring it in the primary. So they will all be stored in the primary memory. And which part? Maybe in the operating system, in the system space, in the system area. Okay, but the point is, everything will not be in the system area, because this is typically a part of I mean, not this one, but I mean the contents, the actual code. So this is not the actual code. So this code segment will point to some page where the code is there. So those codes are in the user space, but these files, I mean these tables will all will be in the system area, right? So even though you see the U area is there corresponding to the green process, but the kernel will not be able to access it. And in fact, they are organized in such a way, these fields here and here, you need not have to, the kernel need not have to actually refer to it. It's not necessary, absolutely. Okay. So this could have been stored here itself, but just to distinguish that there are some entries which are only required when the process is actively running. So to distinguish it, probably the designers have thought of this way out, where they store it in the user area or U area. Okay, I missed the backlink here. I should be adding it. Okay. So now let's come to the process table entries. So the entries that we just now wrote here in almost like invisible. So these are the details, exact details. So the exact details of the entries in the UNIX process table. So what it has got, the process status. This is easy to understand. Pointers to U area and process memory area, like the segment map table and all this. The process size enables the operating system to know how much space to allocate the process. User identifiers, it's a real user ID and the user ID. So different IDs are there. There are different levels of IDs, the group ID, the user ID, the real user ID, the effective user ID. So we can have a discussion on that later on. So there are multiple user identifiers that is maintained corresponding to a process. And process identifiers, this is the specifically the PID and the PPID, ID of the process, ID of the parent process. We know that how a parent process becomes a parent of a other process. This is the event descriptor. This stores the information of on the event, which event actually created it. I mean, created the uh, or forced the process to be in the asleep state. So the reason for that, either it is waiting for a signal to receive, or it is waiting for the disk to be free, or it is waiting to be a file record to be released by some other process. So what exactly? The priority. This priority information, these fields will take care of. So this will be required by the scheduling algorithm. So while discussing about process scheduling, we'll find that what exactly this priority field will store and how it will be utilized, the details of it. Okay. Then the signal. So this is important, and this is something that we just now discussed about. So what it says, enumerates signals sent to a process but yet to handle, but not yet handled. Okay. So it is just like the missed call list you can think of. So I found that maybe say maybe Vivas gave me one missed call, then maybe there are two missed calls from the HOD, and then maybe somebody else gave me three missed calls like that. So so when I wake up, so I was blocked, I was doing busy in some other activities. When I'm when I once again become active running, then I find out what has happened, who sent how many missed calls, and based on that I will take some actions. So this, in the process table entry, it just stored the it just stores the all the signals that it has received but not yet served, handled. And but one information is missing here, that what exactly will be the action corresponding to the signals, that is missing here, and that will be there in the U area. Okay, we'll see that. Then it's the timers. Let's include the process execution time, the kernel utilization time, and sometimes the process wants to send an alarm. So it's like you set start ticking a clock, timer, and when it goes zero, alarm is sent. So these timers are also, you can set the timers and all this. And the p link is a pointer to the next link in the ready queue. Okay, so these are the entries of the process table entry. So the details here we have just expanded it. And then the U area entries, the one that we are telling about, it is a process table pointer, this back pointer. Then the user identifiers, here also it is stored. It is used to determine the user privileges. So again, we'll talk maybe sometime later on the details on the user identifiers. Timers, in this case specifically, it will maintain the time, the record the time corresponding to the user mode and the kernel mode. So how much time the process has executed in the user running mode, and how much time it has executed in the kernel running mode. So those details will be stored here. So it is all related to the running stage. Signal handler array. This is something important. that I was just now referring. Uh, so for each type of signal defined in the system indicates how the process will react to the receipt of the signal. So it can exit. Exit means you can just terminate on receiving the signal. So sig power, SIG PWR. So if you just power off, if you press the power off button, so before it simply goes off, it will send a power off signal like sig power, SIG PWR. It's a valid signal among the list of 64 signals defined in Linux. You'll find that that signal will be delivered to all the other processes by the kernel, all the processes, because that means everybody need to now get terminated because it's a power off, so nothing, so no more execution is possible. Okay, and you cannot ignore it. So there are some signals which you can ignore. Okay, so if I get one missed call from somebody, I simply don't care. Okay, let him give missed calls like that. But if somebody gives two missed call, probably I say, okay, let me ignore it for the time being. I'll later on I'll call him back. But if somebody gives me three missed calls, I know that there's something serious. I'll call him back immediately. And if there is some four missed calls, maybe that I immediately rush to his residence and see that some probably he needs some help from me. So upon receipt of the signal, it can be either in the exit mode, ignore, execute, or you may specify some custom actions. So that corresponding to the entire signal set of signals, you can it's something like the interrupt handling routines. So here it is also signal handling routines that will be uh, stored here. So that will be kept track by the user area, U area. And the control terminal indicates the login terminal of the process if that exists. So if you have executed the process from a login terminal, so that will be entered here. So if it is even if it is a background process executed from a particular terminal, it will have that entry TTY, TTY1, TTY2, whatever. Error field and return values associated with the system calls. If you are executing some system call, like if you are executing for, the parent executed for. So if it is successful, this error field will not be set, and the return value will contain either the child process ID or 0. Okay, so whenever the for call returns and it is in the user again in the user running node, the ECU area, these two fields will be checked and accordingly actions will be taken. Then the IO parameters describe the amount of data transfer, address of the source, and the file offsets for IO, all the IO related details. File parameters describes the current root directory and the file system environment of the process. User file descriptor, it records all the files that the process has opened. So we opened there that file in case of account balance. So if I have opened 4 files, so this file descriptor table corresponding to the user, so it will have entry corresponding to four files. Okay, and that will take you to the pointer to the file record. So the limit fields restrict the size of the process and the size of the file it can write. So there are several limit fields which are mentioned here, and if you exceed the limit, definitely what happens? So that some event has occurred, some maybe exceptional event has occurred because you are trying to exceed the limit, then the kernel will probably initiate or send a signal to you that you are doing some mistake. So either you terminate or you do something or you hang up or whatever. And then the permission modes is to mask the mode settings of the files the process creates. So from these two, as you can see that if you consider the fields that we have discussed here, process table entry as well as Unix view area, it includes almost everything that you need to keep track corresponding to a process. And in fact, that is quite exhaustive. But again, if you see the actual record, or I mean the structure, the fields of the structure that you can find in the Linux, Linux kernel internals, that book, and there are many other websites also. You will get the details of it because it's open source. So you can exactly find out that how it defines the each of these fields, what is the variable, what is the corresponding pointer or whatever. Okay, but this gives you a complete set of information that if you store and maintain and monitor, you can know everything and anything about a process, and each process will have all these information stored while it is active and running. And if it is, if it has terminated, if the process is zombie, the only difference is it will not have this U area, but it will have the, before its termination, whatever values it has got in the U area, a process table, that will be preserved for the parent to, you know, to look into it and take care of it. And finally, it is how the process table entries are organized. In a traditional Unix, it is in form of a table. These are the records. These are the structures. So it's basically array of structures. But in the Linux, it is better. It is alternatively, it is stored in form of a doubly linked list. So these are the structures, and instead of a table array, it's stored in form of a linked list, which has it's a doubly linked list. So this points to this as well as this, the next and previous. So everything is the same. It will have pointer to the U area. It will have pointer to the segment map table, and all these. But how they are, connected to each other, this is in form of a doubly linked list. And because of this, here it is pretty easy to refer to a particular process, right? If I refer to process say 7, so I can probably have an entry here and I can refer to it. But here, because it's linked list, you cannot. If I want to refer to the process say 29, if it is say this one, it becomes very difficult to keep track of it. So to make the make things faster, searching of the process table entry corresponding to a given PID faster, what is the alternative? So each of these processes are unique processes, and they are having their unique PIDs. The colors denote like this. Now, because it's a linked list, doubly linked list, if I want to just refer to 29, the process number 29, maybe this one, or if I want to refer to process number 90, say this one, or process number 2, say this one. So how can I make the access very fast instead of just starting from the beginning and checking one by one? Because a system can have hundreds of such processes. How to make this access faster? Any idea? Got the problem? Hello? Are you getting me? Are you all still there, or hello? Hello?
Sir, we can use a hash map for PID, I guess.
Yes, that is what is done. So it's written here. Okay. So that is the only way to do this, because in case of traditional Unix, it's not a big problem probably. But when you come to the Linux type task structure like this, so it uses hash tables, and it uses hash tables. Specifically, it uses 4 hash tables, and each of, like, for each type of PIDs, one is the normal processes, the thread. These are the thread leaders, thread group leader processes, the process group leader processes, the group leader processes, and the session leader processes. Okay, so there are many specific details, because after all, the system needs to take care of various other aspects. But again, for the timing, you can just guess that there is a hash table, and the hash table, and in fact, I got a document also where it mentioned the exact hash function for that. Okay, so what exactly it uses. And this is the reason why in the Linux type systems, how many processes you can have at most? If you think that almost they're like the PIDs are almost like infinite, so there is no limit, say for example. So how many processes you can have? When it will stop? When the creation will fail? If I call fork and fork fails, what can be the reason for this? In case of a Linux system, what can be the reason? Before that, in case of a traditional Unix system, what can be the reason why a fork might fail? Because you don't have a, when it can fail?
Process number to allocate.
Yes, maybe process number you have got plenty, but you have got some other problem. What is the problem? You don't have a free process table entry, because you need a free slot here. Otherwise, where should you store it? Got the point? So the process numbers are there. There are free process numbers, but this is the problem. And in case of Linux, the problem is here it will go on creating processes till it exhausts the entire physical memory. That is that you can probably use for this purpose, because it's not a table. So table has got a finite size. That is what I mean to say. But because of linked list, it's not having a finite size. It can keep on allocating process table entries, these structures, and that can keep on linking with the previous existing ones. But and it stops after a long while. So you can do one thing. You can just call fork infinitely, and maybe before it calls fork, the number, I mean, using I you can write, so that number, the value of the I, you can dump it in a write mode in a text file. Okay, so or you can also show it in the display in the monitor itself also. So keep on store, and just see that, okay, after 5 minutes, 10 minutes, of maybe 15 minutes, it keeps on creating process, and at some point of time it stops. So what is the maximum process ID that it can generate, that you can have a feel of it. Okay, and this is the last slide. So this talks about the user level context, register level context, and system level context. So this is almost self-explanatory. What I mean to say is, in the user level context, so when I say the context of a process, now you have got a better idea of what a process means, right? You know that what kind of fields the process should have. I mean, we are not just talking about hypothetical and somewhat generic terms. We now talked about very specific terms, and we found the implication of those terms to a certain extent. And I would request you to go through the book by Stallings as well as Buck. So Buck has got only 2 to 3 pages covering this part. I mean 3 to 4 pages, and Stallings also has got like 5 to 6 pages. So once you should read a book, otherwise no matter how much I keep shouting, there are few things I'll always skip, because there is a time constant always. So at least once you should read a book, and then maybe you uh, try to get everything there. I mean, many other things that is not possible in a lecture. Okay, you can correlate the whole thing in a much better way. So here, this is the user level context. It includes the process text, data, user stack, and the shared memory. Shared memory I have skipped. That I will talk sometime later. The register level context, from the name itself, you know that the program counter, the process status register, and the stack pointer. And that is important. Stack pointer actually points either to the kernel stack or to the user stack, as we have shown in the very first few slides. And the general purpose registers, these are the hardware dependent registers and all this. So special purpose registers, general purpose registers, stack pointer, everything, the contents of those belong to the register context. And the system context is process table entry. Definitely that belongs to the kernel space. The user area, which is accessible only when it is running, but it is always maintained for active processes which are not terminated or zombied. Per process region table, these are the all those segment map tables. I mean, every process will have a segment map table, and we have 4 page map tables. So the bunch of 5 tables together forms the process region map table. And then the kernel stack. So that also, the kernel stack frames, initially it will be null, it will be empty, but as and when there is a system call, it will be having some frames. When you come back to the user user mode, it will be again empty, like that. So together it becomes a system level context. So when you think of a context switching, that because of interrupt, because of timer interrupt or some reason, the CPU is switching from one process to some other process which is in the ready queue, in the front of the ready queue, then the context means this, all this information corresponding to the last running or the current running process need to be saved. And so this is basically the context of a process. So the context of process means everything that is actually shown here, and that you can recall back that what exactly they mean in terms of that schematic diagram showing those pointers and all. So context saving means, context switching means saving it and then loading the new one, the newly scheduled process. So this is about context of a process, process data structures, and the process states in terms of Unix systems. Okay, so this is the end of the lecture. I'm switching off the recording. So if you have got any question, you can ask.